Hello, welcome to your lesson on expectation. And let's begin with a game. So consider this game. Two dice are rolled. The difference between the two values determines how you move. So imagine you rolled a 6 and a 1. The difference between those would be a 5. So that's the value you're trying to get. So now you move like this. If the scores are equal, for example, a 4 and a 4 or a 3 and a 3 are rolled, then you move forward 4 spaces. If the two rolls differ by 1 or 2, then you move forward 2 spaces. And if your two rolls are different by 3 or more, then you move forward 1 space. Those are the rules of the game. In an upcoming lesson, we'll look at exactly how to obtain this probability distribution table, but right now we'll just look at it and be given this table. So what this table means, if you remember from the last lesson, is the probability that our move, because we're talking about how much you move equals 1. So the probability you move 1 space is 1 in 3. The probability you move 2 spaces is 1/2. And the probability you move 4 spaces, because that's the other potential move here, is 1 out of 6. Notice we have put 1, 2, and 4 here, which are all the possible values that this random variable m can take. Those are all the possible moves. And those are probabilities. So let's say we're given that. So first question. Let's say the dice are rolled 36 times. Complete this expected frequency table. Okay, so frequency means how many times it would happen, right? So out of 36 rolls, how many times would you expect your move to be a move of 1 based on this given table? And out of 36 rolls, how many of your moves would you expect to be 2 spaces? And then how many would you expect to be 4 spaces? Please fill that in. All right, let's take a look. The answers are 12, 18, and 6. How do we obtain those? Well, we know that 1/3 of the time you will move 1. So 1/3 of 36, or in other words, 36 divided by 3 is 12. So 12 times out of 36 you will move 1. And then 1/2 of 36 is 18. So 18 times out of 36 you will move 2 spaces. And then 1/6 of 36 is 6. Great, so all we did is multiply those by this number here. Okay, let's continue. So now we have the probability distribution table and now the expected frequency table for 36 rolls. So question, calculate the mean of this frequency distribution. So of this one here, calculate the mean. How would you find the mean value? Think about that. Remember when you had expected frequencies, we say a 1 occurred 12 times, and a 2 occurred 18 times, and a 4 occurred 6 times. So how would you find the mean there? See if you can remind yourself. And what does this mean represent? Okay, so here's how we find the mean. We say, again, 12 times 1. And 2 occurs 18 times, and a 4 occurs 6 times. So here we're adding up all the possible things. So 12 ones plus 18 twos and plus 6 fours. We're adding all those possibilities up, and we're dividing by 36, because that's how many total rolls there were. So that answer is 2. Okay, so we just found out the mean is 2. So the mean of these values is 2. What does that mean? What does that mean? All right, what that mean tells us is what your average movement will be. So sometimes you'll move 4 spaces, sometimes you'll move 1, a bunch of times you'll move 2, but on average, you'll be moving 2 every time. That's what that tells you. Okay, so now we're going to do the same thing here. So fill in this expected frequency table and find the mean like we did here. But this time the dice are rolled 100 times instead of 36 times. So what values will go here and what is the mean when you figure that out using the same approach as we did here? All right, this time we have 100 over 3 here because 1/3 of 100 is 100 over 3. And then 1/2 of 100 rolls, half of them will be 2, so there's 50. And then 1/6 of them, 1/6 of 100, which reduces to 50 over 3 instead of 100 over 6. That many of them will be a 4. So how about the mean? Well, the mean, we're going to use the same approach. And notice now we're using mu, Greek letter mu, which represents mean. So the mean is, again, the probability of rolling a 1, or sorry, the frequency, because 100 over 3 represents about 33.3, right, times we'll move once. So that times the movement of 1 plus 50 times will move 2 plus 50 over 3 times will move 4. And you divide by 100 because there's 100 moves in total. And the mean ends up being, well, check it out, it's the same. And that is not coincidental. It's the same. Because the probabilities remain the same, or the proportions of each of these remain the same, it doesn't matter how many rolls you do, on average, you're still expected to only move twice, because this proportionately compared to these two is exactly like 18 was compared to these two. So on average, you will move 2. Tells us the same thing, because the probabilities have not changed. All right, so what would the mean value of m be if the experiment was repeated 10 times, or 1,000 times, or just once? Well, the answer to that is it's the same. The mean would always be the same because the probabilities remain the same. All right, let's move ahead with that idea. That idea leads us to an important formula called the expected value formula. Here's how it works. When we want the expected value of some random variable, in this case m, that represents basically the mean. And the mean can be found by taking the sum, this means sum, of the probability of one of the values occurring times the value itself, and then you add the next one, exactly the process we just followed, and we'll see it in action in just a moment. So for example, so the mean or expected value of a random variable x is the average value that we should expect for x over many trials of the experiment. And here's another form of the formula. This one here had m in it based on our last example, but here it is with using x. So again, expected value of random variable x is equal to the sum of one of the x values times its probability plus, because that's what sum means, the next x value times its probability plus the next x value times its probability, and on until you go through all the values in the probability table. Okay, now let's talk about money. So I have an example or a situation for you to consider. Let's check this out. So this is the situation. You have two choices for earning money over 30 days. Every day you reach into a bag with 3 bills in it. A $5 bill, a $10 bill, and a $100 bill. You keep the bill you pull. So imagine a bag, it has those 3 bills in it. You don't see, you reach in, can't see what you're getting, and you pull out one bill, and it's one of those 3. You keep the bill, you do that every day for 30 days. The second way for you to earn money is this. Okay, so every day you have an 8% chance of getting $1, an 84% chance of getting $2, or an 8% chance of getting $500. So it's very clearly most likely you will get a $2 bill, and then a small chance it'll be a $1 bill or 500. Which option would you choose for 30 days? All right, let's take a look at that in using the lens of expected values. So again, expected value is the mean or average of a random variable over many trials. So we're saying, okay, over 30 days, what happens? What is the mean value you would expect to get per day if you consider this happening over 30 days? So we use this formula. So let's apply it. Okay, so let's do this situation here. Okay, some days you will get $5, sometimes 10, sometimes 100. But over many trials, what is that average daily amount you're expected to get? That's what the expected value calculates for us. So try to calculate the expected value here. All right, here's our formula, and here's how we apply it, right? We do the sum of all the probabilities times the amounts. So there's a 1/3 chance you'll get a 5, plus there's a 1 in 3 chance you'll get a 10, plus there's a 1 in 3 chance you'll get 100. Because each of those is equally likely when you reach into this bag, right? So this calculation will tell us what is that average amount we're expected to get in one trial if you ran this for many trials. So let's take a look what that works out to. That works out to 38.3. So you know, some days you'll get this, some this, but over many days your average amount per day will be this much. That's what expected value is. So not bad, not bad. Let's take a look at situation 2, where you have this tiny chance of getting 1 or 500, but a big chance of getting $2 every day. So there's no way this is going to reach 38, right? Let's take a look. Run the expected value on that. Now when you do an expected value here, it's $1 and there's a 0.08 chance, plus, because we're doing the sum, $2 and there's an 84% chance, so 0.84, and $50, or sorry, 500 times 0.08. What does that work out to? Wow, amazingly, that's slightly higher than that. That was unexpected because there's such a small chance of getting 500 and 92% chance that you get either $1 or $2 per day. But even those few days that will occur raises your average up to this, which surpasses that. Pretty amazing how those expected values work. So again, this is the average you'll get over a long time, because sometimes you'll get 1, sometimes 2, sometimes 1 and 2 again, because these occur often, but that once in a while you get this one and it raises your average up. Okay, let's keep going. Next experiment, or next game, we roll dice 3 times and we count how many 6s are rolled. This looks familiar. So random variable x represents the number of 6s rolled. We've created this tree diagram to represent this before, and we can see to roll 3 6s is very unlikely. To roll 1 6 happens a few times and we get a higher probability, and so on. We created what's called a probability distribution table for that, and it looked like this. So the chance of getting 0 6s is this, the chance of getting 1 6 is this, 2 6s, 3 6s. Great. Find the expected number of 6s. So based on this probability distribution table, what's the expected number of 6s? If you ran many experiments, what's that average number of 6s you'd get? All right, let's check it out. Check your work here. Ends up being a half. Okay, so it's very likely you'll get 0 6s, we can see here, and then less and less likely you'll get more 6s. So therefore, the expected value is a half. Of course, that number makes no sense in this scenario, because you're either going to get 0, 1, 2, or 3 6s, but your expected value is an average. So on average, you'll get not 1 6, not 0, but a half. You'll get somewhere in between that. Okay, next one. Let's try another game. Find the square of the roll. Let's say you roll 1 die, and now the variable that we're expressing here is the square of the result. So let's look at it again. Roll a dice, and the random variable x represents the square of the value rolled. For example, if you rolled a 1, 1 squared is 1. If you rolled a 2, 2 squared is, okay? So if you rolled a 1, sorry, a 1 is one of your possibilities. Now if you rolled a 2, that means 4 is your next possibility. If you rolled a 3, that's 9. If you rolled a 4, it's 16. If you rolled a 5, it's 25. And if you rolled a 6, it's 36 because you square it. Now what's the probability of each of those things happening? Well, they're all 1 out of 6, because this is a normal die, 1 out of 6 chance. So now find the expected value of the roll. What would be expected value? Like, what would be your score, the expected score, I guess, if you did this many times. So run your expected value. You do 1 times 1 6 chance, the score of 4 times 1 6, the score of 9 times 1 6, and on and on. And finally, you find out that your expected value is 15.2. And that makes sense, because these high scores are quite high, these are low, but your average is getting pulled in this direction, 15.2. Okay, next situation. Given this situation, that your expected value of whatever this random variable z is 5 2/3, we are looking to solve for x and y here. This problem is going to be a little tougher. How can you do this? You have 2 variables, you're given expected value. Well, you can definitely write an expected value formula then. How about starting with that? So expected value is that, and then replace in the formula. So 5 2/3 is 1 6 times 2 plus 1 6 times 3 plus 1 6 times 5, on and on with x and y. But this equation has 2 variables, so we can't solve it. So that already tells you right away you're going to need two equations in order to solve 2 variables, to do some substitution. So is there a second equation we can create here? Think back to our last lesson, our last video. Like, what was the thing we were learning there? What did we learn about probability tables there? That's the key to solving this one. Okay, so another equation we can set up is this. We know that when you take all the possibilities in a probability table, the probabilities of all those possibilities have to add up to 1, because if those are all the options, then all the options have to have a full 100% chance of happening. So you add up all the probabilities, they must make 1. Now you have 2 equations. So challenge yourself. Simplify this one. Get rid of that denominator of 6, maybe by multiplying everything by 6. Combine things, simplify it. Simplify this one. Then solve for x or y in the blue one and substitute in here. Work your way. Try this out. Don't quit on this one. See if you can solve for x and y by combining these 2 equations using substitution. Let's check our work. So first I multiplied everything by 6 here to get this. Over here I also multiplied by 6 to get this. Then I simplified that, simplified this. Then I decided to solve for x here. Substituted that into this red one here, the x was substituted in. Solve for y here. And once I have y, I can solve for x as well to get this. Alright, great work if you figured that one out. We'll see you soon.